Let me welcome you to this lecture. We have been discussing about the chemistry of metal carbonyls, and so far we have looked at the kind of binary metal carbonyl complexes formed by different transition metals. At the same time, we have also seen the kind of binding modes of the carbon monoxide ligand in different metal carbonyl complexes. Now, with whatever little we have learned about the metal carbonyl complexes, we should be able to raise two very important questions about the carbon monoxide ligand. The first question that we should ask is the reason why carbon monoxide binds to metal centers through the carbon atom but not through the oxygen atom. As such, if you look at the Lewis structure of carbon monoxide molecule, you will realize that there is a lone pair of electron on the oxygen atom, and that is why one would expect that the carbon monoxide ligand will bind to metal centers through the oxygen atom by a donation of this lone pair of electrons, and that is why it will bind through the oxygen atom to the metal centers. But this mode of binding carbon monoxide is not very common, and instead carbon monoxide binds to metal centers through the carbon center, which is quite unexpected as such. The second question that we should ask is the reason why carbon monoxide forms stable complexes only with electron-rich metals, but the complexes with electron-deficient metals are normally unstable. So, for example, the transition metals of group 4, that is titanium, zirconium, and hafnium, no binary metal carbonyl complexes are reported so far because of the electron deficiency of these metals. Also, carbon monoxide forms stable metal carbonyl complexes when metals are in low oxidation state typically. This is against what we contrary to what we have learned so far about coordination from coordination chemistry, where metals in high oxidation state, the crystal field stabilization energy is expected to be higher, and that is why such metal complexes should be more stable. But it does not happen with metal carbonyl complexes, and instead metals in low oxidation state, generally the ones that we have seen for binary metal carbonyl complexes, metals are in zero oxidation state. So only metals which are in low oxidation state form stable metal carbonyl complexes, unlike what we see in typical coordination compounds. So in order to answer these two important questions about metal carbonyl chemistry complexes, we should look at the electronic structure of metal carbonyl complexes, and during this lecture we will try to understand the electronic structure of metal carbonyl complexes, and at the same time we will try to answer these two questions that we have raised. So to begin with, or to learn about the electronic structure of metal carbonyl complexes, we should first identify the orbitals of carbon monoxide which are going to interact with metal orbitals, and at the same time we should also understand the nature of these orbitals before we go and see how they interact with metal orbitals. So let us now first draw the molecular orbital of carbon monoxide molecule and identify the orbitals which are going to interact with metal orbitals. So let's draw the molecular orbital of carbon monoxide, which has electronic configuration of 2s2 and 2p2, while for oxygen the electronic configuration is 2s2, 2p4. So now when we try to draw the atomic orbitals before combining the atomic orbitals of carbon and oxygen to form molecular orbitals of carbon monoxide, we should realize that the corresponding orbitals in case of oxygen are going to lie in lower energy as compared to orbitals of carbon, because oxygen is electronegative in nature, and that is why its orbitals are more closer to the nucleus. So this is 2s orbital of carbon and this is 2s orbital of oxygen. Both are doubly filled atomic orbitals, and when we combine these two orbitals, we get the molecular orbitals of carbon monoxide, one bonding and one anti-bonding. Let us label these two molecular orbitals as sigma 2s and sigma star 2s. So when we fill the electrons from the atomic orbitals, we find that both of these two molecular orbitals, both the bonding as well as the anti-bonding, are completely filled. So let us now draw the 2p orbitals of carbon and oxygen and combine these atomic orbitals to form molecular orbitals of carbon monoxide. So the first, the sigma molecular orbital is going to form. So that is 2px molecular atomic orbital of carbon and oxygen are going to combine to give us bonding and anti-bonding sigma orbitals. So sigma 2p and this is sigma star 2p. So after that, pi molecular orbitals are going to form. So this is pi bonding and this is pi anti-bonding. So this is pi 2p and pi star 2p. So if we fill the electrons from 2p orbitals in these molecular orbitals, we find that this is how the electrons are filled in these molecular orbitals. Now the HOMO of carbon monoxide, that is highest occupied molecular orbital of carbon monoxide, is the sigma star 2s molecular orbital, and the LUMO, is the lowest unoccupied molecular orbital of carbon monoxide, is the pi star 2p molecular orbital. So this HOMO is filled and LUMO is empty, and now we have identified the orbitals of carbon monoxide which are going to interact with metal d orbitals. Let us now look at some experimental data to understand the nature of these molecular orbitals. So if you take free carbon monoxide, the electronic configuration for the HOMO and LUMO, if we draw for these, that is sigma 2s star 2 electrons in this molecular orbital and pi star 2p 0 electrons in this molecular orbital. Now if you look at the CO stretching vibration of carbon monoxide molecule, what you will find is the mu CO is 2143 centimeter inverse for the free carbon monoxide molecule. Now if you ionize the carbon monoxide molecule, that is you remove an electron from the HOMO, that is the sigma star 2s molecular orbital, and make CO plus, then the electronic configuration will become sigma star 2s1 and pi star 2p 0. And now if you look at the CO stretching vibration of this ionized carbon monoxide species, what you will find is that the CO stretching vibration has slightly increased and it has become 2184 centimeter inverse. What it tells us is that on ionization of carbon monoxide molecule or removal of one electron from this sigma star 2s molecular orbital, the CO bond strength has increased, or the CO bond order has increased, and that is why the CO stretching vibration have now increased. So it essentially tells us that this molecular orbital is anti-bonding in nature, and that is why removal of an electron from this molecular orbital increases the CO bond order slightly. So this is this molecular orbital is, we can say that it is slightly anti-bonding in nature, because the increase in CO stretching vibration is not very substantial. So anti-bonding character of this molecular orbital also must be not very significant, and that is why we write it as slightly anti-bonding molecular orbital. Now if you ionize the carbon monoxide molecule, that is if you excite the carbon monoxide molecule, that is you lift an electron from the HOMO to the LUMO, that is from sigma star 2s to pi star 2p, then the electronic configuration will become sigma star 2s1 pi star 2p 1 because now you have filled an electron in the pi star 2p molecular orbital. And now the species that we have, it has two unpaired electrons we see, and the spins of both of these two unpaired electrons can either align parallel to each other or anti-parallel to each other, and based on that you will have two different electronic structures or electronic states of this species. One is called, we call this a singlet spin state, in which case the spins align anti-parallel to each other and cancel each other. So the total S of a system in that case becomes equal to 0, and spin multiplicity is equal to 1, and that is why we call it the singlet state. Now, if the spins align parallel to each other, that is total spin is going to become equal to 1, and the spin multiplicity in that case, if you use the 2s plus 1 formula, you get is equal to 3, and that is why that is the triplet electronic state. So the CO stretching vibration for the singlet as well as for the triplet electronic states are different from each other. For the singlet, you observe the CO stretching vibration at 1489 centimeter inverse, while for the triplet state, you observe the CO stretching vibration at 1715 centimeter inverse. But what it essentially shows us is that there is drastic decrease in the CO stretching vibration when we excite the CO molecule and lift an electron from this molecular orbital to the pi star 2p molecular orbital, or it tells us the nature of this pi star 2p molecular orbital, that it must be strongly antibonding in nature, as filling of this molecular orbital, unlike removal of one electron from this, changes the CO stretching vibration considerably, because the CO bond strength has decreased substantially, or the CO bond order has decreased substantially when we fill this molecular orbital. So it must be strongly antibonding molecular orbital. So now from this experimental data, we have understood the nature of this molecular orbital. Let us now try to draw these molecular orbitals so that we can see how they interact with metal d orbitals. Now, before we try to draw these molecular orbitals, what we should observe is that the energy of this molecular orbital, filled molecular orbital of carbon monoxide, is pretty close to the energy of this 2s atomic orbital of carbon. What it essentially tells us is that this molecular orbital is localized, or primarily localized, on the carbon atom and not on the oxygen atom. Or the electron density on the carbon atom is more as compared to the electron density on the oxygen atom. So when you draw the contour diagrams, the lobe on the carbon atom is going to be quite large as compared to the lobe on the oxygen atom for this molecular orbital. So when you draw it in such a way that you draw the lobe on the carbon atom larger as compared to the lobe on the oxygen atom. So this is our sigma star 2s molecular orbital, which contains 2 electrons. Now, if you also try to draw the pi star 2p molecular orbital, you will realize that the energy of this molecular orbital as well is close to the energy of the 2p atomic orbital of carbon, and that is why this is also a primarily carbon-centered molecular orbital, and this is pi star molecular orbital. So again, the lobes on the carbon atom is going to be larger as compared to the lobes on the oxygen atom, and this is antibonding. So we should draw the lobes in this way. While in this case also, because this is also antibonding molecular orbital, we can draw the lobes in this mismatch fashion. So symmetry of the lobes mismatch. So now we are done with drawing the molecular orbitals, as well as we have identified the molecular orbitals. Also, we have seen the number of electrons on each of these molecular orbitals, which are now going to interact with metal d orbitals in formation of metal carbonyl bonds in metal carbonyl complexes. So, first is sigma star 2s atomic molecular orbital of carbon monoxide, which is slightly antibonding in nature, is going to interact with metal d orbital, that is empty metal d orbital of the right symmetry again. So d orbitals are Girard symmetry. So we draw it in this way, and because this molecular orbital is now filled, electrons will be transferred from the molecular sigma star 2s molecular orbital of carbon monoxide to empty metal d orbitals to form a metal carbonyl sigma bond. So now it is obvious to us why carbon monoxide binds to metal centers through the carbon atom but not through the oxygen atom, because carbon monoxide forms sigma bond to metals by using a molecular orbital which is primarily centered on carbon atom but not on the oxygen atom. And that is why the interaction or the bond is going to form between metal atom with carbon atom but not with the oxygen atom, and we draw the binding mode of carbon monoxide in this way, where there is metal to carbon bond between metal atom to carbon atom bond in the complexes. So after this sigma bond has formed by transfer of electron density from the carbon monoxide to empty metal d orbital, now what has happened is that the MC bond order has increased, you see, because there is a formation of metal carbon bond now, a sigma bond, and the CO bond order, if you look carefully, because now we are removing electron from a slightly antibonding molecular orbital, CO bond order will also increase when you form the sigma bond, or because of this interaction between these two orbitals of carbon monoxide ligand and metal atom, the CO bond order also increases. Now, after the sigma bond is formed, this pi star 2p molecular orbital of carbon monoxide, which is empty, is going to interact with filled metal d orbitals. So, filled metal d orbitals of again right symmetry, as we have seen earlier, is going to interact with carbon monoxide pi star 2p molecular orbital, and now electron density is going to be transferred from metal d orbital to empty pi star 2p molecular orbital of carbon monoxide to form metal carbon monoxide pi bond. And since the electron density transfer of electron density happens from metal to carbon monoxide, that is why we call this interaction as pi back bonding, or the kind of ligands which accept such electron density from metals in their empty orbitals are known as pi acid ligands, because they accept electron density from metal orbitals. So this interaction now will also increase the MC bond order. As you see, the MC bond order will increase further upon formation of this metal carbon monoxide pi backbone, and the CO bond order now, because carbon monoxide is accepting electron density on a strongly antibonding pi star 2p molecular orbital, so the CO bond order is going to decrease because of this interaction. Upon pi back donation, the CO bond order is going to decrease, or CO bond strength is going to decrease, and that is why you will observe substantial decrease in the CO stretching vibration once metal to carbon monoxide pi back donation happens. Now this should allow us to answer the second question that we have raised, that is the reason why only electron rich metals form metal carbonyl complexes or stable metal carbonyl complexes. The reason being, there is synergy between this sigma bond as well as this pi back donation or pi back bonding in carbon monoxide complexes. The more the metal can donate electrons to the pi star through the molecular orbital of carbon monoxide, or the more the extent of back donation, the ability of carbon monoxide ligand to do sigma donation to metal empty orbital will also increase. So there is, because of this synergy in um, pi back donation as well as with pi donation, the only complex or only metals which are electron rich are going to form stable metal carbonyl complexes. As for electron deficient metals, the extent of pi back donation is going to be less, and that is why the ability of carbon monoxide to form sigma bond with metals will also be less, or it will be compromised, and that is why they will not be able to form stable metal carbonyl complexes. While for electron rich metals, the metal will be able to donate more electrons to the carbon monoxide empty pi star orbital, and that is why the ability of carbon monoxide to again donate to metal empty d orbital to form the sigma bond is also enhanced, and they form stable metal carbonyl complexes. So this has allowed us to answer both of these questions, to the two questions that we have raised in the beginning of this lecture. Now let us look at some more experimental evidences which allows us to see that there is considerable pi back donation in metal carbonyl complexes. The first example, or the first experimental evidence that we will see is in bond distances. So when there is, we have already seen that when there is carbon monoxide forms metal carbonyl complexes, the more the pi back donation, the MC bond order increases while the CO bond order decreases. Now if you look at the CO bond order or the CO bond length, as well as if you look at the MC bond length, so the more the pi back donation, the MC bond length will decrease, and one expects that the CO bond length will increase upon higher pi back donation. Sorry, the bond length will increase. So if you look at the CO bond length in metal carbonyl complexes, what you will find that the CO bond length in free carbon monoxide is equal to 113 picometer, while in metal carbonyl complexes, the CO bond length typically lies near 115 picometer. So there is a difference of around 2 picometer in the CO bond distance in case of the metal carbonyl complexes as compared to the free carbonyl ligand. But the difference is very less, as it is only 2 picometer, and we cannot use such a small difference in bond distance to compare the extent of pi back donation, or compare the extent of pi back bonding in metal carbonyl complexes, as our ability to measure this small distance with high accuracy is also very limited because of the limitation of the diffractometers that we use to measure bond distances. But if we look at the MC bond distance instead of the CO bond distance, and one complex we will see as an example, that is a molybdenum carbonyl complex. The molybdenum nitrogen bond distance in this case is 231 picometer, while molybdenum carbon bond distance is 193 picometer. Now if you take the molybdenum nitrogen bond distance, which is 231 picometer, and deduct the covalent radius of nitrogen, which is 70 picometer from the bond distance, what you will get is the covalent radius of molybdenum, so it will be 161 picometer. Now if you add the covalent radius of carbon to this covalent radius of molybdenum, then you should get the single bond distance between molybdenum and carbon in this metal carbonyl complex. So the covalent radius of carbon is 72 picometer, so this gives us 233 picometer. So one expects that the molybdenum carbon single bond distance in this molecule should be equal to 233 picometer, but that is not the case. So that we observed experimentally, the molybdenum carbon bond distance is equal to 193 picometer, which is 40 picometer smaller than what we expect for a molybdenum carbon single bond. And this shortening of MC bond, metal carbon bond in this carbonyl complex, is because of the pi back donation or considerable pi back donation by back bonding that is present in this complex. So this, by comparing the MC bond distances in metal carbonyl complexes, we should be able to tell the extent of pi back donation in different metal carbonyl complexes. So we have now seen how one can use X-ray crystallography to evaluate the extent of pi back donation in metal carbonyl complexes by measuring the metal to carbon bond distance, as there is substantial decrease in the metal to carbon bond distance upon pi back donation. At the same time, we can also use IR spectroscopy to measure the extent of pi back donation in metal carbonyl complexes, as well as we can also find out the kind of binding mode that carbon monoxide uses in different metal carbonyl complexes, and we can also measure the relative ability, that is pi acceptor ability of different pi acid ligands just by using the CO stretching vibration as a diagnostic tool. So we'll discuss about these things now. The first thing that we should see that is that the CO molecule in free state, the CO stretching vibration appears at 2143 centimeter inverse, while in case of the terminal binding mode of carbon monoxide, when the terminal binding mode of carbon monoxide is present, the CO stretching vibration appears somewhere between 1850 to 2120 centimeter inverse. Now, the reason why in some complexes you see the CO stretching vibration for a terminal binding mode at lower wave number, while in some cases it appears at higher wave number, is the extent of pi back donation in case of complexes, metal carbonyl complexes, where the metal is electron deficient, is going to be less. So the amount of electron density that is going to be transferred from the metal to the carbon monoxide pi star 2p or pi is going to be less, and that is why the CO bond order will not decrease very substantially, and the CO stretching vibration is going to appear at higher wave number. So for electron deficient metals, you see the CO stretching vibration appear at higher wave number even if you have the terminal binding mode. Now for electron rich metals though, you see that there is a larger pi back donation, or the extent of pi back donation is going to be more, and the amount of electron density that is going to be transferred to the pi star 2p molecular orbital is going to be large, and that is why the CO bond order will decrease now substantially, and CO stretching vibration will appear at lower wave number than what you see for complexes formed by metals which are electron deficient in nature. So for the doubly bridging binding mode of carbon monoxide, so the CO stretching vibration appears somewhere between 1750 and 1850 centimeter inverse again. And for the triply bridging binding mode of carbon monoxide, you observe the CO stretching vibration appear at even lower stretching vibration, stretching frequency wave number, that is 1620 to 1730 centimeter inverse. In case of the semi-bridging binding mode of carbon monoxide, where carbon monoxide is considered to be a 6 electron donor, again when it uses the pi bonding molecular orbitals to coordinate with metal centers, the CO stretching vibration appears at even lower wave number, as there is even more decrease in the CO bond order, as it uses the pi bonding molecular orbitals to coordinate with metals to act as a 6 electron donor. That is why the CO stretching vibration appear somewhere near 1350 centimeter inverse for the semi-bridging binding mode of carbon monoxide. So what we have essentially seen is that by just looking at the CO stretching vibration in different metal carbonyl complexes, one can predict which particular binding mode of carbon monoxide is present in those metal carbonyl complexes. So apart from this, it also allows us to compare the extent of pi domination in metals with same number of electrons, or we can also understand the influence of charge on a particular complex on the ability of the metals to form pi back bonding. So let us now look at the CO stretching vibration of some D10 metal complexes. So nickel tetracarbonyl, the new CO stretching vibration in this case appears at 2060 centimeter inverse, while for cobalt tetracarbonyl negative, cobalt is a D9 metal with one negative charge, it becomes a D10, it appears at 1890 centimeter inverse, and for iron, which is as such a D8 metal center, but this tetracarbonyl complex with two negative charge, total there are 10 electrons now in iron d orbitals, and the CO stretching vibration in this complex appears at 790 centimeter inverse. So what you see here is that in all the cases there are four carbon monoxide ligands and only one metal center. So in all the cases, carbon monoxide uses the terminal binding mode, and the number of electrons in the metals are also same in all the cases, but the CO stretching vibration appears at different wave numbers for these complexes. What you see is the negatively charged complex, the CO stretching vibration appears at lower wave number, while for the neutral complex it appears at higher wave number. So the extent of pi back bonding in these complexes must be different, and that is why the CO stretching vibration appears at different wave numbers for these complexes. And the extent of pi back donation is highest in case of the negatively charged complex here, because the CO's bond order has decreased substantially in this case, and that is why the back bonding must be the donation of electrons, pi electron density from metal to carbon monoxide pi star 2p molecular orbital is highest in this case. While in case of the neutral complex, you see that CO stretching vibration appear at comparatively higher wave number because the metal is no longer negatively charged here and it is neutral, and the extent of pi back bonding is lower in this case. So the decrease in the CO bond order is also substantially lower in this case. So this allows us to see the influence of charge on the extent of pi back donation, or what we can say is that just by looking at the charge of on a particular metal carbonyl complex, we have the ability to predict the extent of pi back donation in such complexes. So we can also use the number of CO stretching vibrations that are observed in the IR spectrum of a metal carbonyl complex to predict the structure of the molecule. We have already learned that how one can use group theory to predict the number of IR active vibrational modes in a complex of a particular symmetry. So depending upon the point group it belongs to, the number of IR active vibrational modes are going to be different. So So for example, if you look at facial and meridional isomers of say this type, so this particular complex, it can have either a facial or meridional isomer of the same formula, but the symmetry or the point group in each of these cases are different. Here it is C3b and here it is C2b. So the number of IR active modes, vibrational modes, are going to be different for each of these cases, each of these isomers. In this case, what you see is that you see two IR active vibrational modes of A1 and E symmetry, while in this case you can work out that there are three IR active vibrational modes of 2A1 and 1B1 symmetry. So just by looking at the number of IR active vibrational modes or number of CO stretching vibrations that you observe in the IR spectrum of a metal carbonyl complex, you can possibly predict the symmetry or geometry of the molecule. We will see one last example on application of IR spectroscopy as a, or the CO stretching vibration as a diagnostic tool now to determine the relative order of pi acceptor, relative pi acceptor ability of different pi acid ligands. So for this, what we will see is that let us look at CO stretching vibration of some mixed ligand molybdenum carbonyl complexes, that is molybdenum phosphine carbonyl complexes essentially. That's for this CO stretching vibration. In this case, this is, if we have the facial isomer, A1 as well as E vibrational modes are going to be IR active, will appear, and we can use both A1 and E vibrational mode to, we can compare the both A1 as well as E vibrational mode of these complexes to compare the pi acceptor ability of the ligands, but for here we'll only look at the A1 vibrational modes. So the A1 vibrational mode appear at 2055 centimeter inverse, while for P Cl3 O3 MO CO5, it appears at 1991 centimeter inverse. For the P OMe 3 O3 MO CO3, it is not 5. It is 1888 centimeter inverse. For PH3 O3 MO CO3, it is 1835 centimeter inverse. So what we have here are facial complexes, all of them are, and of the same metal, that is molybdenum, and there are three carbonyl ligands in each of these cases, and the only difference are the co-ligands, that is phosphine co-ligands. In this case it is PH3, PCl3, POMe3 and PPH3. Now if you look at the CO stretching vibrations of these complexes, you see that the CO stretching vibrations appear at different wave numbers for these complexes. So the extent of pi back donation in these complexes must be different from each other, and that is why the CO stretching vibration appears at a different wave number here. So by looking at this, what we can predict is that the pi back donation metal to CO extent of also it increases, it is lowest in this case, but it is highest in this case. So extent of pi is CO metal to carbon monoxide pi back donation is highest in this case, and that is why the CO stretching vibration appears at lowest wave number in this case, while metal to carbon monoxide pi back donation is the lowest in this case, and that is why CO stretching vibration appear at higher wave number in this case. So to understand the reason behind this difference in this CO stretching vibration, we need to look at the orbitals which interact, metal orbitals which interact with carbon monoxide as well as with phosphine, uh, and then we can understand why there is difference in pi connection in these complexes. So let us redraw the metal orbital involved in pi donation with carbon monoxide pi star 2p molecular orbital. So there is pi donation of electrons from metal to metal feed orbital to pi star 2p molecular orbital of carbon monoxide. Now if you look carefully, what you will see is that phosphine ligand also has empty d orbitals, and these empty orbitals also participate in pi donation with filled metal d orbitals. So again, electron density will be transferred from metal to phosphorus empty d orbital to form metal to ligand, pi back bonding in this case as well. So the same orbital of metal now has to donate electrons to both empty orbital of carbon monoxide as well as empty orbital of phosphorus in phosphine ligand. So there is competition between these two orbitals of the carbon monoxide ligand as well as of phosphine ligand to accept electron density from the same metal d orbital. So the stronger pi acceptor ligand will win the race, and that is why if we have a better pi acceptor ligand here, if the phosphine ligand is better pi acceptor, then the extent of pi donation to the CO pi star 2p molecular orbital is going to be less, and the CO stretching vibration in that case will appear at higher wave number. So that is the case what we see over here. The PF3 ligand must be a better pi acceptor, and that is why its ability to accept pi electron density from the metal center is high, so that the extent of pi back donation from metal to carbon monoxide, or the share of electrons at carbon monoxide pi star 2p molecular orbital is now gaining from the metal is less, and that is why the CO, or the extent of decrease in the CO bond order is going to be less, and the CO stretching vibration appears at higher wave number. But while in this case, the PH3 ligand is a poor pi acceptor than the PF3 ligand, and that is why its ability to accept pi electron density from the metal is pretty low as compared to what you see for PF3 ligand, and that is why now the extent of pi back donation from metal to pi star 2p molecular orbital of carbon monoxide is higher. The CO bond order decrease significantly as compared to what you see for better pi acceptor co-ligands here, and that is why the CO stretching vibration appears at lower wave number as compared to what you see for, in this case, the PF3 complex. So this allows us to predict the relative pi acceptor ability of different pi acid ligands just by looking at the CO stretching vibration of these ligands, and from here we can tell that the PF3 ligand is a better pi acceptor than PCl3, which is a better pi acceptor than POMe3, while PPH3 is the is the poorest pi acceptor ligand as compared to all other phosphine ligands over here. So just by comparing the CO stretching vibration, one can come up with the relative ability of relative pi acceptor ability of different pi acid ligands in this case, and the order that has been obtained by following this procedure tells us that the nitrosyl ligand has the highest pi acceptor ability, followed by the carbonyl ligand, and then we have the isonitrile ligand, and then we have PF3, PCl3, POMe3, PPH3, and then nitrile ligand. So we can come up with such a order of pi acceptor ability of different pi acid ligands just by comparing the CO stretching vibration of such mixed ligand metal carbonyl complexes. So this brings us to the end of this lecture. What we have learned in this lecture is we have looked at the electronic structure of metal carbonyl complexes, and this essentially allowed us to answer two very important questions in metal carbonyl chemistry. That is, the first one that we have learned why carbon monoxide binds to metal centers through the carbon atom but not through the oxygen atom. That is because carbon monoxide uses largely carbon-centered molecular orbitals to form metal carbonyl bonds, or the carbon-centered molecular orbitals interact with metal orbitals to form metal carbonyl complexes, and that is why we see that there is linkage between metal and carbon atom but not between metal and oxygen atom in metal carbonyl complexes. The second question that we could answer is why only electron-rich metals form stable metal carbonyl complexes. The reason being the synergy between the sigma bond as well as the pi back bond that is formed in metal carbonyl complexes. As we see that the more the pi back donation, the carbon monoxide becomes a better sigma donor in those cases and form stable carbonyl complexes. That is why majority of metal carbonyl complexes are formed by metals in low oxidation state or metals which are electron rich. And we have also looked at experimental evidence of pi back bonding in metal carbonyl complexes by comparing the metal to carbon bond distances, as well as we have also seen how one can use the CO stretching vibration as a diagnostic tool to understand the electronic nature of metal carbonyl complexes, and then use it also for different purposes. Say here we have seen that how one can come up with the relative pi acceptor ability of different pi acid ligands just by comparing the CO stretching vibration. So with this I conclude this lecture, and thank you very much for being with me during this lecture.